You can expect this question 9 out of 10 times, especially if you're appearing for round 2 or client round. The reason this question is being asked repeatedly because it allows the interviewer to test a lot of things. And I've observed majority of us start explaining how to use iForm file inside the controller. The question is not about how you handle this inside a controller, but the question is how you design a system which is robust enough to handle thousands of users in production. It is also about how you make the system reliable enough to handle item potency, how you scale the system, how storage is going to work. Let's talk about everything in this video. Hey everyone, Shubham here. I've got 8 years of experience as a .NET full stack developer, and I help candidates becoming full stack developers starting from C Sharp and .NET. And I also create content around interview preparation strategy. So let's talk about this question, which is definitely going to come 9 out of 10 times, as I said. Why does this simple looking question become so tricky in the interview? The reason is it sounds very simple on the surface. To answer it in a holistic and correct way, we have to look at it in a holistic manner. We have to step back and ask a very important question. What does large actually mean here? Now, if you look at here, large can, you know, take you in three different dimensions, and all those dimensions represents completely different thing. And the problem which we face while designing will be very different. When a large size file is being uploaded, it has got a very different problem. Right? It has a lot to do with the memory pressure, the network bottleneck, and the timeout. Because when an interview say, let's say 5 GB file, they're not testing whether you know how to save a file. They're testing whether you understand a long-lived connection. Because the connection cannot break. Connection has got to be there. And here's the real architecture question. Where does the data, where does that data live while it is being uploaded? If your answer is inside RAM, you have already created a scaling failure. A file, 5 GB CSV file upload means minute of continuous data flow. That means a long-lived HTTP connection, continuous byte streaming, sustained resource pressure, large size stress three things: memory behavior, network bottleneck, and timer boundaries. If your memory footprint grows with file size, your architecture doesn't scale. The size of the file should not dictate the memory footprint of your API process, right? It is a data flow problem. Our API must remain memory stable while the file is being uploaded. Okay. Now, next dimension which we touched upon was large records. Same file. Imagine the same file, 1 GB, but this time it contains 1 million records. Now, the problem is completely different. Memory might be fine. You might have already managed it. How we do it? We'll talk about it in coming. But this time it contains 1 million rows. Now, the problem is completely different. Memory might be fine. Streaming might be correct, but the processing could become a bottleneck. Large record will actually stress three different things: validation cost, batching strategy, database write amplification. Because when we are writing on database, the right query will actually put a lot of pressure on database. If you're going to validate all those 1 million records synchronously, you're definitely going to block CPU. And if you're going to insert row by row, you will destroy the database performance. If you wrap everything in a single transaction, you're basically increasing the log duration and risk failures. Now, if you observe, you have to tackle these three issues. So how you actually do that? You would need batching, control transaction, and asynchronous process. We'll come to that. I'll show you how we actually fix this. So now you see, initially we started with large file, large size, then we have to tackle with large record, million. That's where we need batching, control transaction, asynchronous process, and so on. And the next dimension is high concurrency because this will break the system stability. Suppose thousands of users are trying to upload at the same time. Now the problem is not size, not records, not concurrency, but high concurrency is stressing three things: thread pool starvation, because your thread pool is gonna be, kept on getting consumed. Now you'll have a limited scaling. You can't scale like anything. And you'll also have a storage contention. So imagine if every upload is blocking a thread, you are exhausting the thread pool. When that happens, when request starts going up, you know, all of the requests are in queues. The latency will spike and definitely timeout is gonna cascade. If your infrastructure cannot scale horizontally, CPU and memory pressure multiplies across all the instances. So every upload right to the same storage path, you create IO contention. Now let's try and understand how we tackle all these three things. L- A large size, large record, high concurrency. Now we already have defined three different dimensions of large. Now let's isolate them one by one and try solving the large file size dimension first. This architectural objective here is very clear. Your API must remain memory stable. And that's exactly where we have to make a very important design decision, buffering versus streaming. So let's break them down. When a file hits your API, there are two ways you can handle the incoming data, one through the buffering and one through the streaming. Buffering happens when the server is waiting for the entire file to arrive and then only process or save it to the storage. Now, pause for a second and think about that. A 5 GB upload, minutes of continuous data, and your API is holding the whole thing. This is not just insufficient, it is unstable. Memory grows while the file size grows. Garbage collector pressure increases, and threads are also held very for the very longer period of time. Under concurrency, it literally collapses. Now let's contrast the same with streaming. Streaming means you are not waiting. You are processing everything in chunks. You process small chunks as they arrive. Let's say the moment a small chunk of the entire file comes, you literally process and store it wherever you want to. Let's say you want to store it on the disk or to the blob storage or wherever they belongs to. Okay. Your API is not trying to own the entire file. It simply processes the data through. It is just here to process whatever chunk it has received to the storage. So buffering makes memory scale with file size. As the size will grow, your pressure on memory will increase. But streaming will keep your memory constant because it will keep on constantly processing all the chunks it receives and it will do the next. It will storage to the local database, RAM, blob storage, wherever you want to. So if you want to take an analogy, think of think of buffering as a filling a bucket. Streaming is kind of a pipe and water is flowing through. Streaming is not an optimization. It is basically a base expectation for any sort of large file, processing. Now let's try and see what actually happens in the production if we implement buffering. A user uploads a 5 GB file, you're buffering it, and your API is ready with, I will first read the entire file and then only process it or move it to the memory. That means this 5 GB file is sitting into the memory, and because of that, memory pressure is constantly increasing and the latency comes into the picture. Second, this is a long lived request. The thread, that particular thread will be occupied until the entire file is processed. Now just imagine hundreds of users are trying to do the same. First of all, so many threads are already occupied and the memory pressure is constantly increasing. Don't you think it is apt to break the system? It will eventually break the system and you're definitely going to get out of memory exception. Thread pool will be completely starved. There will be timeout, health check is going to fail, all the pods will restart, and suddenly your API is down. And this is at the trap. Buffering works perfectly fine in development if you try, because one user, one file, let's say maybe timing can increase and decrease, but it will work. The moment it is in production and multiple users are trying to access it, or trying to upload it, it is failing. It fails 100% because there's a limit of memory and you're not optimizing your memory as well. And that's exactly why we need streaming. Now let's try and handle the same 5 GB file upload, but through streaming. Your API is going to read the request body, and in .NET, this is exactly what request.body is, a continuous flow of bytes. We do not say, give me the whole file first. Give me whatever chunk you have, give it to me, I'll process and stream it to the storage, blobs, disk, wherever you want to. So in streaming, what will happen? Whatever chunk this API will receive, it will process it and it will store it wherever we have configured it, maybe blob, disk, wherever you want to. And because of that, what happens? The file size doesn't grow exponentially. 5 users, let's say uploading the 5 GB each, memory footprint will remain almost constant. The thread, the time that particular thread is occupied is also pretty much predictable. The pressure on garbage collector will be there, but it is predictable. It is kind of a stable one. Streaming makes memory independent of file size. No matter how big your file size is, it is gonna make your memory independent of that file size. That's exactly why even when we are scaling, streaming remains the best option we use. Streaming is not an optimization. We are not just optimizing it, it has become the baseline architecture when it comes to uploading the large file. So conceptually, it makes sense, right? And this is exactly how we implement in code. Let's take another analogy to understand it even more. Buffering means you are downloading the entire file, entire movie first, and then watching it. Streaming is something, whichever position you are in currently, that much has been processed by the API. You must have observed in the movie and all, right? We're not downloading the entire movie on Netflix or somewhere else. We are streaming it. So in chunks, all the bits and pieces are reaching there, and the API is processing it and displaying. So that's probably one of the best analogy we can think of. Buffering is downloading the entire movie. Streaming is streaming the movie in chunks. So if during discussion something of this sort comes, streaming versus buffering difference, make it very clear that streaming help us to make the memory footprint constant. Because of chunking, it is easier to resume where we have left. So that's exactly why I told you not to start with a controller and iForm file and then apply the streaming. No. First of all, discuss all the different aspects which we might encounter. Streaming streaming also decouples the file size from RAM usage. Because no matter if you're uploading a 5 GB or 10 GB, since API is going to anyways receive since API is anyways going to receive them in chunks, they will consider them to be of the same size. So memory footprint remains constant. It doesn't spike up. All right. Now that we have completed large size dimension, it was the first dimension we were talking about. Now we will talk about large record. Because through large size, through streaming, we have achieved memory to be stable. And now the API is protected from RAM explosion because there won't be a spike in the memory because of streaming, right? So now let's shift our focus on a different dimension, which is equally important, which is large record. Large record is not equals to large file, right? Large record means if you look at this CSV file, let's say it is of 200 MB, but it has got 1 million records. The memory is no longer the bottleneck here. Now, this is becoming a database problem where we have to parse, we have to validate, and then we have to write to the database. Transaction cost also comes into the picture. So that's why it is a completely different bottleneck. Let's talk about it. And there's a very famous question you must have heard of. How do we write these many records without killing the database? Because now the problem, as I already said, it's no longer the memory. The file might be perfectly streamed, memory might stay consistent. There could be 1 million rows, and each row might require validation, mapping, business rule, database write. This is not a storage problem anymore. This is a computational and database pressure problem because database will be in the pressure now. So the way we handle it is through batching. So let's talk about batching here. So whenever we upload a file, we need to parse it and then we'll batch it. So let's say if we want to record, if we want to update 1 million records. So instead of doing that, we will insert in different batches. So each batch, let's say, will consist of 1,000 records. And then we will use bulk insert. So how it works is we will not insert the million record at once. We'll break them into controlled batches, maybe 500 or 1000, depending on how you decide. And each batch is one small transaction, small memory footprint, and shorter lock of the threads. And through this controlled transactional lock growth, smaller batches protect the database. And this is exactly how the bulk insert survives in production. Batching protects the database, but not but that protection doesn't mean database can handle unlimited records, right? You are definitely you are putting all the records in different batches, but there is a limit of the size of the database. And since database has got a limit to which it can accept the data, that's where question of writing faster will become less relevant than how we make sure that we don't overwhelm the database. And that's where a sync ingestion architecture comes into the picture. In this one, what happens is whenever we upload a large file, large data set in the API, there will be a message queue who will come into the picture. As databases cannot handle unlimited continuous write, so here's the real issue. What if client waits until 1 million rows are being inserted? Your API thread stays busy, your database connection stays open, memory remains allocated. Under high concurrency, that's a risky thing to do because everything comes to standstill. Nothing is moving. And your client will actually feel that. You can see like everything is stuck. So we stop treating upload as a synchronous task. We separate the receiving the file from processing the data. So file is being received here. And then the moment API receives the file, it does the basic validation, and then it will push to the message queue, and then it returns. So here's how the typical flow goes like. Your API will receive the file, it will do the basic validation, and then it will push a message to the queue, and then it returns. The client doesn't wait for all the rows to be written in the database. The processing is going to happen in the background in a controlled batch manner, which we just talked about. And it will happen at the speed which database is being able to handle. So client should not be waiting for you for the entire file to be written to the database. So you can see this kind of code. That's exactly we use, while implementing the batch processing. It will pick a batch size, let's say for 1000 for this example. Then it will stream records one by one. It will start parsing in a streamed manner. It will keep on adding to a list until it hits 1000. Okay. Since we have set the limit for 1000, until that 1000 point reaches, it will keep on inserting. And in the process of that, through that small batching, it controls write and repeatedly it will be continuously as long as the limit is 1000. So memory is going to stay in a controlled, stable way. And the database will not choke. Now the question is how do we write those batches efficiently? And that's where bulk insert comes into the picture. We do not insert one row at a time. That would destroy the performance because if you start adding one by one each row, it will take so much time basically. It would take so much time. So in order to avoid that, we use bulk operations. For SQL servers, we use SQL bulk copy. What does that give us? It gives us one network round trip per batch, action log group, much higher throughput. Also, we achieve here. Batching controls database pressure. And bulk insert is the one makes the batching faster. If you use batching in isolation, then it will take so much time. To reduce that, we use efficient bulk insert. So since we've understood how to handle large size and large number of records, let's talk about high concurrency. If let's say thousands of users are concurrently writing to the database, how we gonna manage that? Now we have to move to the third dimension, and the third dimension is high concurrency. So far, we have already solved database pressure, that how we resolve it through bulk insert and batching. They write in the batches, they control the rate, right? Batches control the rate. And that works really good if you're talking about only one upload. But what if multiple users are trying to upload it? So before we get there, let's see. This is one of the most repeatedly asked question you can expect in an interview. So the same problem, which is our third dimension of large file, can be asked in a big way that when thousands of users upload simultaneously, what breaks first? Okay, so let's start looking into it. In high concurrency environment, thread management becomes very critical. If your load implementation blocks the thread, you don't scale. So thread blocking has got to be looked into first of all. If you use synchronously file input output, each request holds a worker thread while waiting on disk. The thread is not doing computation, it's just waiting, simply waiting, because it doesn't have the space to go and do that. And when there is a high load, those blocked thread exhaust the thread pool. When the thread pool is exhausted, new request waits. And that's where your API stops accepting a new traffic. And now the memory will not be crash. It's a runtime starvation, right? Because memory is there. But since your thread pool is exhausted and new process are not able to reach there because you were using synchronous one. In order to avoid that, we have to use async streaming. So in ASP.NET Core, we must be using asynchronous file input out. We have to avoid synchronous blocking calls. So how would you implement it? I would use sync streaming and avoid synchronous file IO to prevent thread pool starvation. Thread pool should not get starved. If it gets exhausted, there will be new process coming into the API will not accept it. And then the entire application will kind of crash and you'll see everything seems. So how we protect it? Let's talk about it. So far, we have already solved database pressure, that how we resolve it through bulk insert and batching. They write in the batches, they control the rate, right? Batches control the rate. And that works really good if you're talking about only one upload. But what if multiple users are trying to upload it? In the process, your thread pool is going to exhaust, your CPU usage will be spiked, and memory will be out of memory exceptions you might get. Okay, let's look at how we actually implement in the C# code. So when it comes to synchronous upload, let's look at the code. This looks very harmless, right? That it is also in, using iform file interface. But the copy to is synchronous. This is the one which is going to block it. Now multiply this with thousands of users trying to upload. You don't have thousand threads out here, and that's where thread pool starvation will start, and eventually it will break. But in asynchronous one, copy to async doesn't block the thread. Copy to async will not block the thread. This is exactly the disk. I mean, when the disk is busy, the thread returns to the pool. This is how you scale under concurrency. It's not about the syntax, it's about the freeing up the space for the threads. So asynchronous code help us free a lot of threads which might have been blocked because of the because of the synchronous blocking. So what actually change when you go from async to sync? In sync, threads stays busy during the write. Till the time write operation is not complete, it will be busy. Request will be open and concurrency eats thread. Means one upload will be one thread. You cannot have multiple threads running, right? And thread pool will be drained. But in asynchronous one, you are not just freeing up the thread, also concurrently it will allow you multiple threads, you know, through the write operation, through the thread pool. So now with synchronous one, threads are no longer the bottleneck anymore. Threads will be free and they will continue doing their execution. But even with sync code, you cannot make your hardware infinite. Obviously, you have made your thread pool safe. Through asynchronous code, you have allowed your disk to be free while multiple threads are released. Through asynchronous code, threads are released while disk is doing the write operation. But even with async code, you cannot make your hardware infinite. There's a limitation on hardware as well, right? So if let's say thousands of users are uploading at the same time, CPU still will have some limit. memory still has got limit. Disk is also limited. So what to do about it? That let's say even with asynchronous code, everything is exhausted. Through this, we have protected the streaming. Now let's talk about how to protect the. Now let's talk about how do we manage infrastructure limit, right? Infrastructure is limited, so we have to do something about it. So we have to protect our system, and that's where these things comes into the picture: throttling, controlled concurrency, and so on. So now that you know how to fix thread starvation with asynchronous streaming, threads are no longer blocked. But here's an important part: even correct asynchronous code cannot make your infrastructure infinite. If let's say thousands of users are arriving at once and trying to upload it, then CPU is also limited, memory is limited, disk is limited. So what to do next? We don't let unlimited work enter the system. And that's where we introduce rate limit. But rate limiters, it through rate limit, we will control how many uploads are acceptable, or how many controls are how many uploads are being accepted here. If the system is full, it will return 429. And when 429 is response, and when we are returning 429 as response, it is not failure. It is basically a protection layer against our infrastructure. Because if multiple and so many uploads are going there, our infrastructure can break. So that's exactly how we save our infrastructure through rate limiting. We introduce rate limiter and we introduce throttling. So I hope this made sense that rate limit help us to protect our infrastructure through throttling. Throttling simply means you are slowing down. Throttling simply throttling simply means you are slowing down your incoming traffic. That's all. And this is how you implement it, right? You just have to create a. I mean, you have to use a add rate limiter middleware, and you configure it as per your requirement. Now let's talk about scaling out, not scaling up. What does this mean? Now, protection is not enough all the time, right? We have seen how sometimes protection is not enough. We also need to scale our system. And scaling is something which is being done by the load balancer. We do not scale vertically. We basically scale. We don't scale vertically. We basically scale horizontally. Vertical scaling means adding more and more, let's say, database, infrastructure, and all. But in but here, using load balancer, we are doing it horizontally. We are creating multiple APIs which will be handling different things. So till now, we have also protected the system using rate limiting and throttling, but protection alone doesn't increase the capacity. So if the traffic grows, we need more processing power. And to achieve that, we introduce a load balancer. A load balancer is a load balancer is going to sit in front of our application, and its job is simple. A distributed, it will distribute the incoming request across multiple servers. If you see the three boxes here, they are identical API instances. In production, we never run a single API server, right? We run multiple instances of the same server. Instead of one powerful server, we run multiple smaller servers working together. Okay. Now we notice something important here. All three API instances use the same storage, either S3 or blob storage. That storage could be anything, S3 or maybe Azure blob storage also. This API instance can accept the upload, whether it is for S3 or maybe for blob storage. So single API instance will take care of any sort of storage we want to. And after this file is created, we push a message to the shared queue. This queue. This queue will coordinate background processing. So it doesn't matter which API instance handles the request, the processing pipeline remains consistent. This this kind of design removes dependencies. No local file, no instance specific state. Every servers behave the same. All three of them. It will be stateless, and it will be using shared storage and shared queue. And that's exactly how in today's world modern system work. So whenever you are asked this question, so next time when you encounter this question, make sure to give them the entire end-to-end picture. Keep this image saved with you because it's an extremely important image which has got everything. So if you look at it from the naked eye, it looks so big, so complicated. But when you're discussing the same thing during interview, you have to break them down one by one and then recollect everything to give an impression what are the things you will be discussing about. So let's revisit once whatever we have talked about and how to answer this question in a holistic manner. So now we have understood what large file actually means. In production, it's not just about loading a file, it's a memory management, concurrency, storage limit, and system scalability. Everything came into picture. And without even you realizing, and without even you realizing, you have understood a lot of follow-ups which you're going to face during the interview. So let's look at the complete flow. This Angular client sends a request to upload the file. The user starts from the client application. The browser upload the file in chunks with resume, support, and progress tracking. The request first hits the edge layer, which is CDN, Content Delivery Network, and security. This will take care of TLS termination, basic protection, and edge routing, right? And then it reaches to load balancer, where it will distribute the load to different API servers. When we reaches here, it will have the upload API stream in file asynchronous. And here we will be having no buffering. We will be having asynchronous streaming, rate limiting, authentication enforcement, and everything. And then worker and batching will do background work, which will parse it, transform it, and validate. And whatever it is to write, it will write in different batches. So the client only uploads the file, it doesn't wait for processing. And now by knitting everything together, eventually the file, no matter how big in size, how many rows, or how many users are trying, we will be able to handle all this scenario in a single, we will be able to handle all this scenario gracefully. And if this question is being asked, you will be able to explain everything, not in isolation, but in a holistic way now. We have to cover a lot of follow-ups still waiting for the based on this question. So let's see you in the next video where we will be covering more scenario-based questions and also some follow-ups which often comes around this topic as well. And one of them is, and one of the repeatedly asked, and one of the repeatedly asked question around this topic is, how do you handle idempotency? Okay, we already have answered it, but I will give you the holistic picture in the next video. Let's come back in the next video and understand everything. Thank you for subscribing. Keep on sharing and liking the video. Thank you.